I built a small flight computer in C. This flight computer is able to track the initial position of the flight, it is able to track the final position of the flight, and as it is moving from the initial to its final location, it is also able to track its current position while it's moving. It tracks the amount of air pressure that is being exerted on the computer as it navigates towards the target destination. And most importantly, it also manages to track the direction it is moving in using vectors. Now, let's get into the code. Since this has been made in C, I have also utilized inline assembly in order to make the mathematical performance much faster and better. The logic flow is a little something like this. So we use this good old generic formula to find the distance between the starting point and the target point. Now then we also calculate the relative position vectors. What does that mean? What that means is that if, say for example, our problem looks a little something like this. We start from this point and we are headed towards this point in the 3D space. So generally the approach is, in order to move from the red point to the green point, we simply go from the red all the way towards the green. Now we are using relative position vectors. What does that mean? What that means is that we draw a line starting from the origin to a starting point. We then draw a line starting from the origin to the target point, and using these two lines, which are also vectors for that matter, we then draw a third line that goes a little something like this. Now this final red line, this is our relative position vector. All that remains is for us to move these points to their better suited locations, and we get something that looks a little something like this. This red point, it moves from here to the origin, and a line of the length of this red line right here is drawn from here all the way to target. So this target comes here and our initial point moves to the origin. So this green line right here, this is what we call the relative position vector. And then we find the initial velocity using this formula for the 3D space. And this is a big part, this is a big highlight, as we're using assembly for it. We're directly telling the computer the exact instruction it is supposed to follow in order to evaluate the initial velocity. Then as we're moving forward, we use these formulas to determine its initial velocities in all the three axes. We then use these generic equations of kinematics according to Newton in order to determine the position, velocity, and the components. And now comes the phases, right? So the phases are a little something like this. As we are moving this, and we are moving from, say, our initial point to our, say, final point right here. So the path that we're using a very reliable projectile motion. Now the projectile motion looks a little something like this. We start from the origin here, we move up to this point. This point is the maximum amount of height that we follow. Now once we've reached this point, we then move all the way down here. This is our phase 1, and this is our phase 2. Now phase 1 is what we call the acceleration, because we are moving upwards, so our speed is increasing right here, and we use these formulas to determine the velocity and the acceleration and the position. And then when we are deaccelerating, what that means is that right here we are now moving down towards the target, the phase 2 right here. So for the phase 2, we have similar formulas that are mentioned right here, and as usual we also account for gravity. Now what's important here is that the sign of the acceleration changes. we now flip the sign of the acceleration, because now we are moving downwards. As we're moving downwards, we have to flip the sign of the acceleration right here, because even though in the magnitude it remains the same, acceleration is still a vector and it's now moving in the negative direction. So we have to denote that. Anyway, then lastly is the quaternion rotation. How does that work? What that looks like essentially is a little something like this. We have, what is the point of this? The point of this is to determine the angle that our projectile is moving in. And how do we determine that? Well, we draw one vector, this red line right here. This is our velocity vector, and this line right here, this green line is our vector that points towards the target. Now, with these two vectors in mind, we are able to find their dot product and then use this formula in order to determine the angle right here. With this angle, we are then able to determine the axis of rotation, and with the axis of the rotation, we are then able to form the quaternion, that is a number which represents the this right here. This is actually supposed to be a vector that denotes the rotational components of our projectile as it is moving towards the target. And then we also evaluate the pressure. We use this barometric formula, and the way this barometric formula has been implemented in code is that, yeah, right here. We first evaluate the temperature. After we found the temperature, we then find the pressure using this formula, and these are the constants that we have used within the program right here. And then as we're moving at every point in time of the motion, we also evaluate the velocity, the distance from the origin, and the axis and the direction. And of course, since we have to continuously evaluate the time as well, so we evaluate the current time, the time taken from the beginning, the amount of time that takes up deceleration, acceleration, and that is about it.
This has all been made in C using absolutely nothing else besides C and a little bit of inline assembly. Thank you.